Welcome back. We're going to talk now about solving systems of linear equations, and along the way I'm going to talk a little bit about linear transformations. And please try and ignore the fact that I misspelled the word transformation at the top of all of the slides. So going back to the beginning of the course, let's recall what we were doing. We started with a system of linear equations, for example a 2 by 2 system like this, and the first thing that we did is we converted it into a matrix equation like this, and then we talked about techniques about how to solve such a system, and in particular we used Gaussian elimination to replace this equation with a simpler one, which we were then able to solve easily. And so in this case the solutions turn out to be x is 1 and y is equal to 2. And for now I want to point out that this second step here with the matrices, up till now it's all we've really thought of this as a way of conveniently storing the coefficients of the equation. We haven't really used much about matrix algebra here. And so now I want to talk a little bit more about these kinds of matrix equations and the structure of their solutions. So that brings up the topic of linear transformations. I'm getting a little bit ahead of ourselves here. You should see section 1.6, but I'm only going to use a little bit about linear transformations here, and I'll talk more about them later when we get to section 1.6. So let's go back to matrix multiplication. I went over this kind of quickly earlier. Let's say a little bit more about it now. You can multiply two matrices when? Well, you have to have that these two numbers are the same, the number of columns of the first matrix and number of rows of the second. And if those are equal, you think of those as canceling, and the result is you get an M by R matrix. Well, so for example, if you take R is equal to 1, you see the following. You can take an M by N matrix and multiply it by an N by 1 vector, and what you get is an M by 1 vector. In other words, this matrix A that we're talking about is really a function. It's a function from Rn to Rm. If you plug in an n vector, you get out an m vector. And this matrix, this function that we're getting here, is an example of a linear transformation. And I'm not going to talk much more about linear transformations at the moment. That's in section 1.6. They satisfy various properties, but for now we're just going to use these matrices and have these matrix equations. So the point is that we can think of a matrix equation like this: ax is equal to b as the following. Well, x is an n vector and b is an m vector, and so ax is equal to b. What this says is that you have a map from Rn to Rm, and you're given a vector in Rm, that's b, and you're looking for a vector in Rn which hits it when you apply A. So that is to say, finding x, what you need to do is find x so that A takes x to b. That's the way you think of this equation. So here's an example. Suppose I take the 2 by 3 matrix like this and consider this equation like this. xyz is equal to 5, 0. So xyz are unknowns. This is a map from R3 to R2. And I'm given the vector 5, 0 in R2, and I'm asking, can I find a vector in R3 which hits it when you apply this matrix A? Well, never mind actually solving the darn thing. Let's just ask, when can you solve it? How do you know if you can solve it? And let's look at this left-hand side. If you multiply it out, you get, if you multiply the matrix times the vector, you get x plus 2y, y plus 2z, and x plus 2y plus z. And you're trying to set those equal to 5, 0. And now here's the key point. You can rewrite the left-hand side in a sort of nicer form, which is x times 1, 1 plus y times 1, 2 plus z times 2, 1. And we're trying to make that equal to 5, 0. And look what we have here. These vectors on the left-hand side are exactly the columns of the original matrix. And this equation is saying that we have a linear combination of the columns of the matrix, and that linear combination is equal to 5, 0. That exactly says that the vector 5, 0 is in the column space of A. So we talked about the column space a little bit last time. I'll remind you, if you have A is an m by n matrix, the column space is, well, you just take the columns and you consider their span, the columns. And since those are m vectors, the column space is a subspace of Rm. So the picture is the following. We have this matrix A, and we're thinking of it as a map from Rn to Rm. We have the column space of A is a subspace of Rm, and the row space of A is a subspace of Rn. For our purposes now, it's really the column space we care about. What we've shown is that if you have an equation like this, Ax is equal to B, where A is m by n, and these are size n and m, this has a solution if and only if B is in the column space of A. Now, there are a couple of natural questions which arise. How many solutions are there, and how do you find them? And a natural question is, the solutions are in Rn, do they form a subspace of Rn? Okay, well, let's look at a special case. Suppose this vector b is equal to 0. So we're looking at the equation Ax is equal to 0. So that's exactly saying that x is in the null space of A. And the word null space is basically telling you something. It's answering the question that, in fact, the solutions is a subspace. In other words, if Ax is equal to 0 and Ay is equal to 0, well, if this is going to be a subspace, you better have that Ax plus y is equal to 0. Is that true? Well, yes, because A of x plus y is Ax plus Ay, and both Ax and Ay are 0, so their sum is 0. So this thing is clearly a subspace. Scalar multiplication is similar. So the answer to question 1 is yes in this case. If b is equal to 0, sorry, that's question 2, the solutions form a subspace. If b is not equal to 0, the answer is no. The solutions to Ax is equal to b is not a subspace, because if Ax is equal to b and Ay is equal to b, well, what's Ax plus y? Well, it's Ax plus Ay, which is to say b plus b, which is to say 2b. And avoiding any jokes about 2b, 2b is not equal to b unless b is equal to 0. So this is not a subspace. Now, on the other hand, if b is not equal to 0, look at these two equations. Ax is equal to b and Ay is equal to 0. And so I've put a different thing on the right-hand side here. Now, if you add x plus y, that is a solution to the equation. You get Ax plus Ay, which is to say b plus 0, which is equal to b. And if you think about it a little bit, you see the following. In order to solve the equation Ax is equal to b, find all of the solutions to this equation, what you do is you find any single solution called the particular solution, call it xp, so that is to say Axp is equal to b. And then what you see is that every solution to the original equation is of the following form. It's x is equal to xp, the fixed one, plus xh, where xh, h stands for homogeneous, is a solution of the associated homogeneous equation ax is equal to 0. So you find all of the solutions here, all of the solutions to the homogeneous equation, a single solution to the particular equation, and then all solutions are obtained by adding those. And this problem down here, solving ax is equal to 0, is the one we just discussed, the special case we just discussed, and that gives the subspace. So what we conclude is the picture looks something like the following. In R2, suppose I'm trying to solve ax is equal to b, well, I find a particular solution, some non-zero vector xp, and suppose all of the solutions to the homogeneous equation are a subspace, so they look like this subspace, say, of R2. So that's the solutions to the homogeneous equation. Well, then the solutions to the original equation are just obtained by shifting this, by adding xp to it, and what we get is this line, this blue line, consists of the solutions to the original equation. So it's not a subspace, but it's a translated subspace. You take a subspace and you move it by a single vector, or a shifted subspace. So to reiterate, we have two problems. We need to solve the homogeneous equation ax is equal to 0. That is to say, x is in the null space of A. And we need to find a single solution, a particular solution to the non-homogeneous equation ax is equal to b. So let's talk a little bit more about the first part, where we have a homogeneous equation. And here's a basic example. Consider this equation. So we have a 3×4 matrix of this form. So we're taking a 4 vector to a 3 vector, and we're trying to solve this homogeneous equation. And so A is a map from R4 to R3. Now, let's write out what the left-hand side is. It's x plus 0y plus z plus 2w is equal to 0. And 0x plus y plus z plus w is equal to 0. And then there's the last equation, 0 is equal to 0, which of course I can ignore. So I'm trying to solve this set of equations, and it's very easy. If you just divide it in half, you see the following. The variables z and w can be anything you want. And because no matter what you take them to be, you can then solve the first equation for x and the second equation for y. So z and w are called free variables, and then x and y are the dependent variables. So as I said, you can solve for x and y in terms of z and w like this. That is to say, this is a two-dimensional space of solutions because you have two free variables, z and w. So let's look at a little more closely at why this worked so easily. Well, this matrix that I have here is an example of a matrix in reduced row echelon form. And what that means is that these two numbers here are pivots. They're both 1, and everything above each of those pivots is 0, above and below each of those pivots is 0, which is to say you have a little identity matrix here. And then everything to the right doesn't really matter. Once you have this little identity matrix, that gives you the dependent variables and the free variables. So the strategy is going to be to apply row operations. If you're given an equation, apply row operations to the matrix A and try and put it into reduced row echelon form. And if you can do that, then you can see what all the solutions are, what the dimension of the space of solutions is, and so on. So let's look at an example. You take this 3 by 4 matrix, and you do the usual thing to kill off the first, the entries in the first column below the first one, and you get this. And now you can kill off the third row by adding the second row to it, so you get this. And now we're going to do something new. We're going to go back. We're going to use the second row to kill this -1 in the first row. And what we get is 1, 0, and 0, 1, and then some other stuff to the right. And now we're in reduced row echelon form. So we see we have 2 free variables and 2 dependent variables, so the solution space is going to be 2-dimensional. And you see that x is equal to -2z minus 3w, that's a misprint on the w there, and y is equal to -4z minus 2w. So z and w are arbitrary, and they determine x and y. So in order to describe this space, you can pick 2 vectors in it, and as follows, set z is equal to 1 and w is equal to 0 to get x is equal to 2 and y is equal to -4 and 1, 0. Or set z is equal to 0 and w is equal to 1 to get the vector -2, -2, 0, 1. That's 2 vectors in the space of solutions. So the space of solutions is exactly the span of these 2 vectors, and so that makes it clear it's a subspace and it's 2-dimensional.